Hi there. In this video we're going to calculate another derivative of a function, and in this example we're going to look at the function 2 over x. Okay, a little bit of notation before we move on here. There's many ways to express a derivative. Two of the more conventional ways of doing that is this: f prime of x and dy over dx. Some people just say dy dx. Of the two, this one probably means more in terms of its notation. The dy simply stands for the change in y. What is the change in y over the change in x? And if we go to the graph, this makes much more sense. By now this picture should look familiar to you, and as this secant line slowly becomes a tangent line, when we're finding a derivative, what we're really saying is what is the change in y over the change in x? What is the slope of the tangent line at any particular point? Okay, so now in this example, I've gone ahead and I've let my initial x value be 1. Okay, this guy is at 1. So if I wanted to evaluate the derivative at 1, I would bring this other point very close to it, and I want you to understand that even though you can't see my triangle that I've constructed in here, the triangle really is there. It's just infinitely small. Okay, this value right here represents the change in y, and this expression right here represents the change in x. So you can see that at the point 1, when x equals 1, it appears that the change in y over the change in x appears to be right around -2. Okay, so again, just to reiterate, the derivative of this curve at 1 appears to be -2. Another way to think of it is the instantaneous rate of change. The instantaneous rate of change. Okay, well, how do you find this instantaneous rate of change? Now, on our graph we found it when x equaled 1. In other words, just from the graph, we concluded that f prime of 1 equals right around -2. Okay, now I wouldn't solely rely on the graph to determine that. We're going to rely on our limit process to do that for us. Okay, so this is what we got from the graph. All that's saying is that when x is 1, the slope of the tangent line to our original function is -2. So let's go ahead and calculate the derivative then of this function. Not at 1. We don't care about 1. We want to know what is the derivative, the slope of any tangent line at some generic point x. Okay, and we do that by evaluating this limit right here. By now you should be familiar with it. Okay, this looks familiar from our graph. All right, let's go ahead and evaluate this limit. Well, what is f of x plus h? And f of x plus h is going to be 2 over x plus h. Our input is simply x plus h. Okay, minus f of x. Well, what is f of x? F of x was defined for us. That was just 2x. And this is all over h. Okay, so you may try to evaluate this limit right now, and if you did that and you substituted 0 in for h here and here, you would get 0 over 0, and that's our indeterminate form that we know we have to change. Okay, so the way I'm going to change this is by dealing with these complex fractions. And the way I deal with complex fractions is I simply multiply everything by the LCM of what I call these complex denominators. Okay, so what's the LCM of x plus h and x? Well, it's just x plus h times x. And I usually put a 1 over it just to help people see the multiplication that's going to occur here. Sometimes it's hard to see why things cancel the way they do if we don't do this. But anyway. Okay, so really, this is a great big disguised 1. We're really multiplying this expression by 1. Okay, so here's why we chose the LCM. when I multiply these first terms together, notice that the x plus h cancels. I'm really left with 2 times x. So I get 2x. Now, if I multiply times the second term, notice that this x will reduce with this x, and I'm left with a negative 2, this negative 2 here, times x plus h. And this is all over h times x plus h times x. Okay, well, going further, we can reduce, or we can simplify the numerator. If you notice that this is, if we distribute this through, you'll notice that this is a negative 2x. It's going to cancel with this guy, so that's effectively going to be 0. And I'm really just going to be left over with this negative 2h. So negative 2h up top, down below. I'm not going to distribute for reasons you'll see here in a moment. Okay, so here's what I have now. Notice I still have an indeterminate form here. Whoops. Goes to 0. There we go. Now, you'll notice that I have an h in the numerator, an h in the denominator. They reduce, and I'm left with the limit as h goes to 0. Up top I have negative 2, and down below I have x plus h times x. Okay, so now it looks like we're all ready to use direct substitution to evaluate this limit. Let's go ahead and substitute 0 here, and in the numerator I just get a negative 2, and in the denominator this is just 0, so x times x is an x squared. Okay, so what is this thing I just found? This is the derivative of my original function. Well, what does that mean? What does it mean to be a derivative of a function? Well, this new function, notice that this is a function in and of itself. This new function tells me the slope of any tangent line to this curve at whatever point I choose. Okay, so this is the slope of any tangent line of any point I choose. For instance, if I wanted to confirm that the derivative at 1 really is negative 2, I can plug 1 into x here and get negative 2 over 1 squared, and whoops, that should be a 1. And negative 2 over 1 squared really is negative 2. So it looks like my derivative checked out. Now the beauty of finding it in this way, and not remember in past examples we said, well, what if we wanted to find the derivative at 1? And we went through this whole limit process. We let x be 1, and at the end of our limit process we would get negative 2. Well, what if you wanted to come back and find the derivative at 2? You certainly wouldn't want to go through this whole process again, changing the 1 to a 2 and then doing all of the same work over. So we find the derivative in general, and now we have a nice little formula that will tell us the derivative at any point. I simply plug in 2 and evaluate. And it looks like we get negative 2 over 4, which is negative 1/2. Okay, well, what does that mean? What does it mean when I plug 2 into the derivative that I get back negative 1/2? Well, that means that negative half is the slope of the tangent line to this curve at the point 2. Let's check it real quickly on the graph to see if that checks out. And all I'm going to do is move both of my points to 2, or at least close to 2. And I'm going to look up at my calculation to see if it's 1/2. And sure enough, the change in y over the change in x really is negative 1/2. In other words, the instantaneous rate of change at 2 is negative 1/2. Okay? I hope that made sense. We will see you later.